Welcome to part 7 of this series of presentations about the best methods to convert aldehydes into secondary alcohols. This video is about the use of boron enolates as carbon nucleophiles. Upon reaction with aldehydes, boron enolates can form a closed, six-member transition state, which often provides for a high degree of stereochemical control. No additional catalysts are usually required. The resulting cyclic boron derivatives are also more stable than the corresponding alkali enolates, and their hydrolysis to hydroxyketones can require harsher conditions and some additional reagent. With dialkyl boron enolates, an oxidative workup with hydrogen peroxide is often used. Boron enolates are usually prepared from ketones, a tertiary amine, and an electrophilic boron derivative. The stereochemistry of boron enolate formation has been carefully investigated and can often be controlled to a high degree. Ethyl ketones, for instance, often yield E-enolates upon treatment with tertiary amines and dicyclohexyl chloroborane, while treatment of ethyl ketones with tertiary amines and titanium tetrachloride generally yields C-titanium enolates. Boron enolates can also be prepared by treating silyl enol ethers with boron derivatives, by oxidizing vinyl boranes, and by reducing alpha-beta unsaturated ketones with boranes. The sketch is not quite correct, as for the latter strategy there's a methyl group missing in the boron enolate. The main advantages of the use of boron enolates as carbon nucleophiles, if compared to alkali enolates, is the lower basicity and increased chemical and stereochemical stability. Then, aldol additions with boron enolates proceed already at low temperature under mild conditions, and few side reactions are usually observed. This leads to high yields and high stereoselectivity. Disadvantages can be the high price of some boron derivatives, what restricts this chemistry to the production of fine chemicals. This is a typical aldol addition of a boron enolate to an aliphatic aldehyde. The reaction conditions were exceedingly mild and a high yield of the expected alcohol was obtained. Here, two equivalents of a dialkyl boron triflate were used to prepare the boron enolate of a carboxylic acid. Again, the aldol addition proceeded already at low temperature, without the need of any catalyst, but the diastereoselectivity was low. Interestingly, boron enolates containing additional secondary alkoxy groups sometimes show a high degree of 1,5 induction, as in the example on this slide. Moreover, a clean addition to the carbonyl group of the alpha-beta unsaturated aldehyde occurred, without any conjugate addition to the alkene. This same reaction with the corresponding lithium enolate only gave a weak 1,5 induction, and with the silyl enol ether almost no 1,5 induction occurred. Thus, when working with structurally more sophisticated starting materials, it can be worthwhile to compare various types of enolates, because the stereochemical outcome can vary a lot. So, what are the potential side reactions? Boron forms relatively strong bonds to oxygen, but also to carbon. And with some types of CH-acidic starting material, during boron enolate formation, also carbon may be borylated. This can happen when converting acetic acid derivatives into boron enolates. This twofold activation can then lead to a twofold aldol addition, as shown here. The boron enolates of carboxylic esters may also undergo an oxygen-to-carbon migration of boron under certain reaction conditions. For instance, upon treatment with catalytic amounts of a nucleophile such as a phosphine. As discussed in the second video of this playlist, the resulting alkyl boranes do not usually react as carbon nucleophiles with aldehydes, but are sensitive to oxidants and to protonolysis. Here's a short selection of some more examples and a review article. The next video is about silyl enol ethers, which are still more stable and easier to handle than boron enolates. See you there.